Hi, this is Dr. Isan Abdullah with the course Data Structures, Algorithms, and Generic Programming. The topic which we are covering is algorithms and analysis. The subtopic is complexity analysis. So, therefore, it's lecture 4B. And the supplemental material is available at ezmcq.com/goget. So, this supplemental material is basically a learning management system which has very features special for personalization of your learning experience. The details are given in these videos, how to use them. Summaries are here. So I would suggest that you make use of those videos. So now we move on to this supplemental website. Okay, so we are at the supplemental website and we are at question number 6 because the first 5 questions have been covered in the lecture 4A. So we have the next 5 questions here. So total 10 questions. So total 10 from 16 is. So the question number 6 is give a comparison of standard complexity functions in analysis of algorithms. So we look at the standard complexity. Of course, there can be others also. So these are the standard ones. There are others also. So let's look at the answer to this question. So we have different types of standard complexity functions. Constant time, linear time. This constant does not mean that there has to be a 1 here. There can be a k here also, and k can be any number, which is not related to the input size. So linear time, because the power, this is a polynomial, the power is 1. This is logarithmic time because the log is here. Linear rhythmic time, n product of log of n. Quadratic time, the power is 2. Exponential time, there is no polynomial here, and this is also not a polynomial. Of course, this grows very, very fast as compared to this one. So let's look at the details. So the details, you can basically click on it and see the details here also. So constant time basically the same constant time amount of time regardless of the size of the input, regardless of the size of the input. Okay, so for example, if I have an array and the array size is n and I want to read the contents at a certain address by the index, so reading that content at the index is nothing to do with the size of the array, independent of it. So that's why it's order 1. So there's no relationship. Okay, so as n increases, the time taken remains constant. Time taken remains constant, so there's no relationship between the n and the size of the and the time taken. Time over here is the number of steps. Remember that. Time is the number of steps. Okay, so now let's look at linear time. So linear time basically is the time grows linearly with the size of the input. So it's kind of a directly proportional. So linear search in an unsorted array. So we have an array which is unsorted and we're looking for something. And in the worst case, which is order O, we end up searching the entire array. We may or may not find what we were looking for, or we might find it at the end of the array. So that's a linear time. So the time increases proportionality to the size of the input. Doubling the size of the input doubles the time. Doubling the size doubles the time. Okay, that's the thing. Then is the logarithmic time, which is order log of n, right? So, so that reduces the input size exponentially in each step as compared to linear time. So, for example, binary search in an S in a sorted array. So, if it's a sorted array, we look at the middle, and depending upon the middle value, we look at the higher values or the lower values. So that takes order log n time. So if n was say 1,000, so linear time, this number of steps are 1,000. But for logarithmic time, if n is 1,000, so log of n to the base 2 is about 10. So so binary search in a sorted array. As n increases, the time grows very slowly as compared to order n, right? Okay, so doubling the input size only adds a constant. So the doubling the input does not doubles. Doubling the input only adds a constant amount of work. Does not doubles, which was the case in linear time. So this is better. Then is linear rhythmic time. Linear rhythmic time basically is a product of n and product of log of n. Like in merge sort and quick sort, the time grows faster than linear but much slower than quadratic. Much slower than quadratic. Okay. So for example, if we again consider the case of n is 1,000. So when n is 1,000 for order n, it is 1,000. For log of n, it is 10. And for log of n log n, so this is 1,000 into 10 is 10,000. Okay. But if it was quadratic, it would be in a million. So this is much better than a million. All right. So quadratic time generally involves two nested loops. So for example, the inner loop runs the number of times as per the index of the outer loop. So maybe it runs for once, then twice, then 3 times, 4 times, so on up to n times. So if you take the sum of all these iterations, so that is n into n minus 1 divided by 2, which is n square minus n divided by 2. So the dominant term is n square. So order n square. Examples is selection sort, bubble sort. All right. So the growth is quadratic. So if the input size doubles, the time taken increases by a factor of 4. This is much slower as compared to linear. Slower in the term that it takes more time. All right. So it's better that I clarify the thing. All right. So order 2 power n exponential time. Exponential algorithms have their time which grows exponentially with respect to the input size. For example, solving the Fibonacci sequence recursively. A small increase results in a large increase in time, making these algorithms impractical for large inputs. Okay. And exponential time, again example. So this is n power n. So variable power variable. This is constant power. This is not a polynomial. This is also not a polynomial. So these are slow and impractical for most real problems. Okay. To give you the example is the traveling salesperson problem, which is a very of practical utility. But even small increases in n causes the time to explode. So for example, n when n is 1,000, so 1,000 factorial, I think it's a very big number. So so to be very precise, 1,000 factorial consists of uh, 2, 5, 6, 7, 8 something digits, very big number. So what we can see here that as the input size increases, the number of steps for constant time remains unchanged, right? And as the input size increases, there is a proportional increase in the number of steps for linear time. And with reference to the n naught, we can see that for this value of n naught, before that, n log n, you can see is growing, is not a better option. But after this, order n log log n is a better option, and so on. So what are the standard notations for complexity analysis of algorithms? So this is the notation. Okay. So I will briefly describe these notations, show you a diagram, and then we go into more details. So this is how we uh, describe them. Is t of and the time complexity is order of f of n. The time complexity is big omega of g of n, and time complexity is big theta h of n, and time complexity is small o p of n. So these are definitions. Remember that. So T of n is we say T of n is order f of n if they are positive constants c and n naught. So this is the c, this is the representing the slope, and n naught is the value after which T of n will always be less than equal to c of fn. So after this, f of n is always less than equal to c g of n. So we say that f of n is order g of n. So this is the upper bound. Okay, and this is the n naught after which forever f of n will be less than g of n. So we say that f of n, we don't say f of n is less, we say f of n is order g of n as per this definition. Then we have here is a big theta. So big theta is kind of an envelope. So there are two constants, c1 and c2, okay, and f of n is between them, and the better would be the case if this distance is minimized. And then we have big omega. So big omega is the lower bound. So f of n, okay, is f of n is always greater than equal to c g of n for a constant c and n naught. So we said see that f of n was going up and down than c g of n, but after n naught, f of n is always greater than c g of n. So we say that f of n is big omega of g of n. Okay, so these are the bounds, right? And these are the description of these bounds which I've already described to you. So now what I will do is I will look at some example and then explain to you based upon that example. So I have zoomed in here. So we see that f of n is n squared plus 5, and this f of n, this is a complexity function. This is not order. This is a complexity function. So the big O bound for f of n could be order n squared. Why? Because this n squared dominates this entire function. N squared dominates this entire function. So for example, if you are taking a course in a semester, you have multiple courses, and there's a course with 4 credit hours inclusive of a lab, and there's a course which is like the directed study 1 hour. So if you look at the number of courses, the number of courses are 4, but the course which has 4 credits, that dominates everything. Okay. So we are more concerned about, and we are spending more time on the 4 hour course as compared to the 1 credit hour course, right? So this is how we look at it. So we of course n squared plus 5n would be one way of doing it, of telling it, but the shape of the curve is dominated by n squared, not by, this is linear, this is quadratic, big difference. So when n is 1,000, this is 5,000. but this is 1 million. So 1 million is very, very significant as compared to 5,000. 5,000 is insignificant. Big omega as a lower bound. Now, when we look at this again, so n square, because n square is the minimum rate of growth for big omega, but the actual function grows faster than n square. Why? Because 5n is added to it. So big omega is not a tight bound. The tight bound is big theta. Okay, big theta, because the large n, the term n square dominates and the 5 1 term becomes insignificant. So big theta, so this big theta is a better bound. All right, so what are the three rules of the analysis of algorithm? So let's look at those three rules. So those three rules are basically, this is the sum rule. So if we have two functions and we look at their summation, so less formally it is the max value, the function which grows at a higher rate. For example, n square plus 5n, so n square, max of n square and 5n is n square. And you take the product also for them in the form of nested loop. So that's n square. So outer loop is running n times, the inner is also running n times. So rule number two, if t of n is polynomial of degree k, then t of n is equal to theta n power k. So for the case of n square in the previous example. And when the power of the log, then it is order n for constant k, right? Because this only changes the constant number. So this is actually the thing, and this is the constant, this is the variable. So this is how we look at the typical growth rates and rates, and this is basically how we name them. So we conclude this subtopic of analysis by doing, so what we have done basically, that was formal kind of complexity analysis. We cannot go into further details because this course is not about analysis of algorithms, but this example would explain some useful concept. So this is g of n. So for your understanding, I have created this in Excel. So n is the input size starting from 1 to 19. So 10 n square, you can see the numbers here, and 100 plus n, you see the numbers here. It does carry a lot of meaning until we plot them. So when we plot them, we see that when n is about 11, when n is about 11, before that, the linear is a bad choice because it is more than the quadratic. But after that value of n, so the linear is a better choice and quadratic is the bad choice. So the concept of n naught, which I described earlier, and the concept of c is the slope. So depending upon the slope, and of course this thing has a corresponding representation. So that's all I have for this subsection on the analysis, and thank you very much.